Okay, so welcome back. We are now in Chapter 5, 5.1 for PreCalc 2. And what we're going to start moving into now is a little bit of the analytic trigonometry. And the first, let me take just a second to kind of build this chapter for you. So for Chapter 5, there's 5 sections, 5.1, 5.2, all the way to 5.5. But the two most important sections, in my opinion, are the first ones, 5.1, and the last one, 5.5. The other three sections, 5.2 through 5.4, they have important elements to them, but in terms of the mastery, they're fairly simple sections. And it's more or less 5.2, 5.3, 5.4 is more or less just, hey, here's the formula, just put it to use. Okay, 5.1, this is an extremely important section. So let me start this way. So let's go back to just algebra. And I want to make sure you understand the difference between solving and verifying. Ready? Let's start with solving. So if we were going to solve this equation, you and I know what to do here. So the goal is to get x by itself, so we would distribute this 5. We would end up with 15x plus 10 minus 4 is equal to negative 24. We would end up with combining the 10 minus 4, so we'd have 15x plus 6 is equal to negative 24. Subtracting 6 from both sides, we'd have 15x is equal to negative 30. And finally, dividing both sides by negative 15 would give us x. Let me make sure. I don't know why I dropped a negative symbol here. Let me go ahead and get rid of that. Would end up with x is equal to negative, 2? Okay, so more structurally, just to make sure you understand. So this type of solving, this type of equation, we end up with what we call a conditional equality. Okay, it's one of the lowest forms of equality in mathematics. So in other words, this equation is equal under the condition that x is equal to negative 2, right? That is, it is conditioned in order for this equation to be equal. Now, a higher form of equality, okay, a much higher form of equality is what we call an identity. Let me show you what I'm talking about here. So it's the same type of problem. Let's just assume that the student begins, this just like we did in the last one. We'd have 15x plus 10 minus 4 is equal to 15x plus 6. And notice at this stage right here, a student could notice that the left side of the equation is identical to the right side of the equation. Now, some students still might not notice, so they might continue trying to solve for x. So if you were to subtract 15x from both sides, you would end up with 6 is equal to 6, a true statement. If you were to subtract 6 from both sides, you would end up with, say, 0 is equal to 0, a true statement. Now, I want to make sure, so typically, I'm going to erase this little part here. So typically what happens when you have an identity, you use, instead of using the equal symbol with 2 underlines, we use this triple underlined equal symbol. And this is basically stating that what you have is an identity, right? These are identical. It's an unconditioned equality. No matter, in other words, let's go back up here with me. No matter what you pick for x, no matter what you plug in, you would get an equation that it's equal, that's balanced. Okay, so this is an unconditioned equality or an identity. Now, so the next thing I want to do is I haven't yet sold you on what it is that we're going to be doing. So we're going to be verifying identities in this section. And I'm yet to tell you the why. Like, why would you spend time doing this? So if you don't mind, let me just punt. Let me hold off for just a second on the why. And let me kind of talk to you about the how for just a second. So we're going to start with some strategy. All right. So if you enjoy puzzles, then you might really like this section. But even if you do not enjoy puzzles, the utility of what we're going to be able to do in later maths is important. So you want to make sure you follow me. So let me start with some strategy. So I'm going to be somewhat informal here, but one strategy is to pick the more complicated side to start with. All right, so start with the more complicated side. Another strategy, I'm going to give you a few of them, then we will add to it. So when you're asked to verify in this section, we're going to make use of the identities. Now, if this were a classroom setting, I would have given you a formula sheet with all of these formulas and identities on it. Now, in the online section, you'll have to go to Canvas and look for the formula sheet for this class so that you can grab, and you might even want to print that out so you have access to these identities. Let me give you two more early strategies, and then we'll add to it. So I don't know why I went from 2 to 4. Maybe you. So one strategy is, after you've chosen the more complicated side, turn. Again, I'm just trying to be informal here. Turn every function, in other words, into sine or cosine. Okay. And finally, we this will become more apparent when we start one. But finally, you don't want to stop until fully verified. Okay, so let's go to our first example. So notice this does not say solve. Okay, that's section 5.5 will be about solving for x. This is verify. So the goal in the game is I need to make the left side look like the right side. Okay? So I need you to understand the rules of this game, because you're gonna pick the more complicated side. So in this case, that's somewhat arbitrary, but we're gonna choose the left side. Okay. Sometimes it's hard to, since it's somewhat arbitrary to say which one is more complicated. What I really mean is which side is busier, right? There's more going on the left side of this equation than on the right side of the equation. Okay, so the next strategy is we're going to use our identities, and I'm going to be calling from your formula sheet. We're going to use some identities to turn this left side, turn everything into sines or cosines. Okay, so hopefully you have your formula sheet out and you can follow along. But secant x is the same thing as 1 over cosine of x. Cotangent of x is can be rewritten as cosine of x over sine of x. Now, at this stage, we've successfully transformed everything, the secant and the cotangent, into functions dealing with only sine and cosine. Again, just easier, a lot easier to deal with sines and cosines. So now, hopefully what you're seeing is that this cosine in the denominator is going to cancel this cosine in the numerator. So that would leave me with, so after my cosines cancel, I would be left with 1 over sine of x. And finally, if you were looking at our trig identities, 1 over sine of x can be written as what? Well, it can be written as cosecant of x. So now I need to make sure you understand how I'm grading this when I grade it. So the best way for you to view this is you are engaged in an argument with me, okay? And just like in any argument, if you were arguing with your mom and dad, say, you don't want to reach your conclusion without justifying your conclusion, right? You wouldn't want to say, well, I want to go watch the movie because why? Well, because I just want to. You would want to be able to justify every step of the way as you engage in this argument, right? So when I'm grading it, what I'm doing is I'm saying, okay, well, this individual, I agree with this statement, okay? I agree with the premise here. Oh, I agree with this statement. Therefore, oh, well, I have no choice. I must agree with your conclusion. Now, what I can't have you do is I can't have you jump steps, right? Don't do that. Don't leave it to me to try to fill in your argument. I need you to go step by step and not stop until you have fully verified. I hope that makes sense. That's what I mean by don't stop until it's fully verified. And lastly, just to really quickly make sure you understand, we choose the more complicated or busier side because it's a lot easier to uncomplicate than it is to complicate, right? It's just a little bit easier. I hope that makes sense, but there's nothing left to do except jump in and continue in this section. Ready? So we want to verify that sine of x multiplied by tangent of x plus cosine of x is the same thing as secant. All right. Now, after I get done with this problem, I'm going to come back and try to sell you on why what we're doing is important to higher maths. Ready? So notice we would choose the more complicated side. So I would choose, say, this left side. It looks a little busier. The first step I might do is turn everything into sine and cosine. So let's see here. So I can sine of x, and let's go ahead and change our tangent. Tangent can be written as sine of x over cosine of x, and plus cosine of x. All right, so far so good. We've changed the left side of the equation into sines and cosines. Now, what we're going to do at this point, so again, since this is kind of a game, we're trying to come up with some rules. So what we might try, let me go ahead and multiply. Let me try to multiply this. Sine of x times sine of x. This ends up becoming sine of x squared. Oh, my apologies, I wrote that incorrectly. So sine squared x divided by cosine of x plus cosine of x. Okay, so if you don't mind, kind of relax for just a second. I'm going to go back to that page where I was listing some strategy here. So with that previous problem, we have already chose the more complicated side. We've already used our identities to turn everything into sine and cosine. But notice that what else are we allowed to do? Well, you can always, another option, you can always combine fractions. That's allowed. Okay, so in this case, we would be allowed to combine these two. So I can, if you like, if it makes it easier, I can write cosine as cosine of x over 1. And now let's think about how we would proceed here. So I'm going to scoot this equal symbol to the right a little bit, give me a little bit more space. All right, so if I have two fractions, I want to be able to combine them, then I need a common denominator, right? So in this case, the common denominator would be cosine of x. So I want to multiply by cosine of x over cosine of x. All right, let me go ahead and simplify this. So now at this stage, I have sine squared x over cosine of x, and that's going to be plus cosine squared x over cosine of x. Okay, so all of that work just to have a common denominator, and now I can take now I'm able to add my fractions. So I'm going to go ahead and add my two fractions, and what I'll have at this point is going to be sine squared x plus cosine squared x over cosine of x. All right, and if you don't mind, just follow me up here. All right, so it's common in these verifying identity problems to start to second guess yourself, right? Like you can imagine, at least I can imagine me when I was first learning this stuff, working and getting to this part and thinking, man, what in the world? I must have done something wrong. But listen, as long as you have not done an illegal operation, you will get there. You will get this thing verified. Okay? Let's just keep going back and using the strategies that we're writing down. So take a look, if you happen to have your formula sheet in front of you, take a look at your formula sheet and see if there's any way that, or what you could do with sine squared of x plus cosine squared of x. Right, there is a Pythagorean identity somewhere in there that says sine squared plus cosine squared is equal to 1. So I can rewrite that numerator as just 1 over cosine of x. Okay? If I went too quickly, where did this 1 come from? The 1 came from the fact that if you look at your formula sheet, sine squared plus cosine squared is equal to 1. All right, and finally, we're almost there. What is this last step? Well, 1 over cosine, 1 over the cosine is secant. That's so at this stage, there's my triple equal symbol. We have verified our identity. And now, if you don't mind, I'm going to take a second and try to sell you on the why here, okay? Because why take time to learn this? So I'm assuming if you're in this class, I'm assuming you have a math, at least in your road of education you have in front of you, you have some, if not many, math courses in front of you, okay? Especially calculus, right? Maybe you're going to have me for Calc 1, maybe you'll even have me for Calc 2, Calc 3, or higher, just depending on where you're going in your career. But one thing's for certain, let me, if you don't mind, I'm gonna call upon a calculus concept. Ready? So I don't expect you to understand what I'm writing here, but that's okay. You will when you're in a calculus class. So there are going to be times when you're going to have a function that you might want to integrate this function, you might want to take derivatives of this function, you might want to graph this function. All I want you to see is notice something. Notice that if I took the left side of the equation and placed it here. Well, this student, if the student tried to integrate it the way it sits, they would have some work in front of them, right? It's not impossible. But if you give me two calculus students side by side, right? One calculus student is working really, really hard, okay, filling their page with work and getting to the answer. And then you have this other calculus student who just seems like they're just just seamlessly getting to the answer and much faster? Well, I'll tell you, it's not IQ. What's happening is the second student noticed that they could, instead of trying to integrate sine of x, tan of x plus cosine, this second student is noticing, wait a minute, I can turn this into secant. So the second student is simply noticing that I can rewrite what's inside this integrand. I can rewrite it as just secant. And now this is a whole lot easier to integrate. I hope you understood what I just said. If you didn't, let me see if I can say it simpler. This: would you rather graph the left side of the equation or the right side of the equation? If you had to get out a pen and paper and try to graph it, wouldn't it be a lot easier to graph it if it looked like secant? It's the same way with integration. This would be a whole lot easier to integrate if you can make it, if you can verify that you could rewrite it as secant. So that is the why behind some of the things that we're doing. Let's continue here. All right. So notice that this particular problem, the left side is busier, so we'll start with the left side. But also notice that, wait a minute here. The left side of the equation is already in terms of sines and cosines, right? So what else should you do? Interesting. So there's no fractions. So you can't combine fractions. There's no identities to grab right from the way it sits. You've already turned everything into sines and cosines, right? So what else? Let's go back to the strategy. What other rules do you have at your disposal? Right? Disposal. So here is something else. Here's another strategy that you can use. You can always try factoring. All right, that's another strategy that you can use. All right, let's finish up the next two problems, and then I want to tell you what you can't do. All right, that's sometimes much more important. So, all right, so what I'm going to do is I'm noticing that both of these terms have a cosine in it, so I'm going to go ahead and factor out my cosine of x. And let's see what's left. Well, if I factor a cosine of x out of cosine, I'm left with 1. And if you factor out cosine from the second term, I'm left with sine squared. All right, so not verified yet. Doesn't look like this side yet. What do you do from here? Well, if you look at your formula sheet, look for how you can rewrite 1 minus sine squared. It's in the Pythagorean Identities. I'll let you look at it if you have your formula sheet in front of you. But what you should see is 1 minus sine squared is equal to cosine squared. So what we have at this point is cosine of x times this 1 minus sine of x turns into cosine squared. All right? And yeah, I know what you're thinking. You got it from here, right? Cosine times cosine squared is equal to cosine cubed. But don't stop, right? If you stop right here, I'm going to take off some points, right? Because I want you to argue all the way to your conclusion, right? Therefore, if I agree with all of your premises, I have to agree with your conclusion. But if you stop right here, it's like having an argument. You have this great argument, but you never actually tell the person what your conclusion is, right? No, don't do that. Conclude it. Finish it. Finish the argument. So cosine cubed of x, and now you're done. All right. So let's do another one. I'm going to add to the strategy list, and then I want to come back and talk a little bit about things you cannot do. All right, so let's take a look at our problem. So notice that I tell you, if you ask me which side's more complicated, I'll say I don't know, right? Because it is somewhat arbitrary to say which side is more complicated. I just don't really know another way of making that statement except using that informal language. So in this case, you could choose the left side and make it look like the right side, or a student could choose the right side and try to make it look like the left side. Either way is fine. Let's go ahead and start with the left side. Okay, so the goal is to make the left side of the equation look like the right side of the equation. All right, so let's start. So we're looking at this left side of the equation. There's no identities to use. There's nothing to factor. Everything is already in terms of sines and cosines, and there's no fractions to combine. Right? So, in other words, we need another strategy here because none of these are going to help us. So that's okay. So the good news is another strategy that you can try when you start to run out of ideas is try to break up a fraction. In other words, try see if you can turn one fraction into two fractions, right? So let's see how we would use something like that. So right now we have one fraction, and it's that fraction is 1. I'm going to go ahead and erase that yellow line. I don't want that to confuse anybody. So that one fraction is 1 plus sine over cosine. So we're going to split it up. So that can be split up into 1 over cosine of theta plus sine of theta over cosine of theta. All right, so we've split up our fraction. So now we're always looking to see if there's any identities that we can use. And we're basically at the end at this point. 1 over cosine, that is the same thing as 1 over cosine is the same thing as secant. And sine over cosine is the same thing as tangent. So right here, we're done. We have verified our identity. Okay, so if you don't mind, let me take a second to tell you what you cannot do. Right? So so just like any game that you're going to play, there's rules that you have to use, and here's some rules that we can't do. All right, so do me a favor, pay attention. Let me see if I can go to. We're going to take a break in just a second, but let me go ahead and do this now. So I'm going to give myself a little bit of space, and if you've started to daydream a little bit, if I could just have you come back for just a second, I'm going to make sure that you know what you cannot do. So, are you ready? So let's start. So I understand that our properties of algebra, rules of algebra, they allow us to, say, subtract cosine of x from this side, subtract cosine of x from this side. Right? What I'm doing here, that is, algebraically, this is perfectly legal. It's perfectly a legal operation. But what I'm telling you is that's not the game that you're playing. You're not playing the let me solve for x game. That'll be later in this chapter. And what you are doing is you're going to take it the way it sits. You want to see if you can make this left side look like the right side the way it sits. Just like if you were to follow my example up here. When you're trying to, say, integrate something, you don't have the option of with what's inside the integrand. You don't have the option of doing, adding, subtracting from both sides of the equation. You want to be able to integrate the way the function sits, and that's the same thing here. You want to be able to integrate the way it sits. Last, before I take a break, what are some really bad, well, how do I put this? So what are some bad strategies, common bad strategies? So a lot of times when students are verifying, the most common one is they don't go all the way, right? They stop before finishing the problem, right? Before concluding the problem. That's one mistake. Or they write really sloppy in hopes that I won't be able to read it, but I won't take off points. skipping skipping steps, like jumping right from here to here without the skipping of steps, or making stuff up. you know I just want you to understand, I will sit down when I grade it like you and I were having an argument, and I will go step by step. So every step, if I can't read your handwriting, that's not my fault. Just like if you and I are having an argument, if you're using a different language than me, that's not my fault. It's not my fault. Or let me restate that. If you are using language that I don't understand, maybe you're using really large vocabulary words and I don't understand it. It's not my. You could argue it's my fault that my vocabulary is not enhanced enough, but you are trying to argue with me, right? You're trying to convince me of something, so you'll have to use language that I understand, because I can't get convinced unless I understand what you're saying. So just like you'll have to you'll have to justify every step of your argument. You can't just jump to the conclusion of the argument too fast and expect me to agree with your conclusion. Does that make sense? I hope that makes sense. We'll go ahead and take a break, and we'll come back and we'll finish this section.